So let us solve a problem on bending and shear stress. Examination problem in this class. So the question runs like this: a simply supported beam, 100 mm by 200 mm, 100 mm by 200 mm. That means 100 mm width and 200 mm depth. In cross section carries a central concentrated load, W. The permissible stress in bending and shear. The permissible means allowable or maximum. Permissible stress in bending and shear are 15 MPa and 1.2 MPa respectively. 1.2 MPa respectively. Determine the shear flow W. Determine the shear flow W if the span of the beam is 3 meters. If the span of the beam is 3 meters. So this is an examination problem. So let us see how we can solve this. So solution runs like this. A simply supported beam 100 mm by 200 mm, that is the cross section. So let me say rectangular beam. So 100 mm is the width, 200 mm is the depth. So width I will take it as B, depth I will take it as D. So naturally the centroid lies at the umbilical center, neutral axis passes through the centroid. So suppose if this is used as a simply supported beam over a span of 3 meters. So 3 meters is the span, that is L. And if a central concentrated W is applied, central concentrated means exact center is 1.5 meters distance. So let me take the points as ABC. A and B are the supports and C is the mid-span. At the mid-span point, there is a load W, constant load W is acting. He has given permissible stresses in bending and shear. That means maximum bending stress available, permissible is 50 MPa or Newton per mm square, whereas maximum shear force, shear stress, Qmax, is 1.2 MPa. This is given. So what is the value of W? How much the beam can carry safely the concentrated load? That is the question. So first thing in this type of problem is an analysis type problem, whereas we have to find the unknown load. First thing we have to locate at what point you have maximum bending moment and at what point of the beam you have maximum shear force. Because we know that maximum bending stress occurs at the point of maximum bending moment, maximum shear stress occurs at the point of maximum shear force. So in the case of a simply supported beam, you know from the concept of bending moment and shear force, in this case, maximum bending moment occurs at C. That you have studied in BMD and assembly chapter. Under this load, when the load is acting, it occurs and its value, Mmax value, that is MC value, is WL by 4. So this is standard formula for centrally concentrated load. Maximum bending moment in the case of a simply supported beam is WL by 4. Here L of course is 3 meters. So I can take that L as 3 meters or 3000 mm. So this is one thing, because all the units will have to stick to newtons and millimeters, because stress value is in newton and millimeters. Similarly, maximum shear force supports, that also you know, occurs at either A or B. Both A and B, because it is symmetrically loaded. And its value, so that is F max, will be FA or FB. That will be equal to W by T. So this is the maximum shear force. So now he has also given the values of maximum bending stress and shear stress. So we know that for applying the pure bending equation, we have to take this moment value. For applying shear stress equation, we have to take this shear value. So that is very important. So when you are applying pure bending equation, you have to take this value for M. When you are applying shear force shear stress equation, you have to use F max, that is W by 2. Of course, he has restricted the stress values here. F max is 15 MPa and Q max is 1.2 MPa. So now let me tell you how the bending stress and shear stress diagram will be across the section. So you know that in the case of the rectangular section, bending stress is maximum at the farthest fibers, the extreme fibers. That means you can see bending stress diagram. We have learned in your earlier classes also. So this is how the bending stress distribution will be. At the neutral axis, F will be 0, whereas it is maximum here. Since it is simply supported beam, compression will be there at the topmost, that is fibers above the neutral axis, and tension will be there in the fibers below the neutral axis. So Ft max and Fc max, of course, here in this case, they are equal because it is symmetrically loaded. That means its section is also symmetrical. This rectangular section is symmetrical section. So this Fc max in this case will be equal to Ft max. This is only the case of rectangular section. Is equal to 15 Newton per mm square. This is just given. This is the bending stress distribution. So at the point C, if you take the cross section, there you will be having this maximum bending stress, Fc max and Ft max, as it is allowed. Only 15 Newton per mm square is allowed. Similarly, if you draw the shear stress diagram for this rectangular section, shear stress diagram will be like this. Maximum shear stress occurs at the neutral axis, whereas shear stress is 0 at the farthest fibers. Q is 0 here, 0 here. Here Q is Q max. So you know that at the neutral axis level we have the maximum shear stress. At the neutral axis level we have the 0 bending stress. So that means these two things we have to make use now. This value and this value. Of course, here he has given Q max value as 1.2. It should not exceed 1.2 Newton per mm square. So that means for using this bending stress equation, we have to take section C, section at C. So this is at section C, at the point C. Whereas if you to use this shear stress diagram, because shear force is maximum on the supports A and B, so this section will be at section A or B. So please note that it is not at the same section. In this case, bending moment is maximum at C, shear force is maximum at A and B. Therefore, for analysis, we have to consider the section at C for bending, section at A or B for shear. Now let me go one by one. First, I will consider this pure bending equation applied at point C. Pure bending equation applied. This should be applied at section C. It has to be applied at section C. So the equation states like this: M by I is equal to F by Y, or this F by Y can be written as F max by Y max. When F is max, F is equal to max, Y will be Y max. Now, we don't know the value of moment here, but moment can be expressed in terms of W. So M is WL by 4 here, where L is 3000 divided by I value is BDQ by 12. So please note that for rectangular section, moment of inertia about the neutral axis or the centroidal axis is BdQ by 12. So where B here is 100 mm, D here is 200 mm. So 100 into 200 cube by 12. This is I is equal to F max value. I have to take 15 divided by Y max value is nothing but distance of the farthest fiber. So this is Y max. This can be Y max, or you can take this also Y max because of symmetry, which is 100. 200 divided by 2. This is total is 200 divided by 2. So it is 100. So this is the equation we got. From this, let us find out the value of W here. So W will be equal to 15 into 100 into 200 cube divided by this 12 goes to numerator, 12 into 3000 into 100. So this is the value of W. Now let me simplify this. This 100 will get cancelled with this 100. So if I simplify this, I will get W as 15 into 200 cube divided by 12 divided by 3000. So you are getting 3333.33 Newton. It will be Newton. Please note that 3333.33 Newton. And W will be Newton. So this is from the consideration of bending stress. Considering the shear stress equation, because he has given both the values, we know that Q is equal to F into A y bar divided by IB. This is the expression for shear stress. So since I have to take Q max, so Q max occurs at the neutral axis level. So to find A y bar, I have to take the area above the neutral axis or below the neutral axis. So of course here it is same. So A y bar I need now. A y bar is equal to A is area above the neutral axis, which is this is B. This is D by 2. So B into D by 2. So B into D by 2 is A into Y bar. Y bar is the distance of the centroid of this. Suppose if you look at the centroid of this shaded area, distance of that centroid from this D is Y bar. So B into D divided by 2 into Y bar. So B into D is B is 100, D is 200 divided by 2 is 100 once again. Y bar is half of D by 2, that is total is 200. So this depth is total depth is 200. So this will be half of 100, that is 50. So this is the value of A into Y bar. If you simplify that, you will be getting 10,000 into 50, 50,000. 50,000 millimeter. Unit is millimeter. So this is A y bar. I value we have got BdQ by 12, which is I calculate here. B is 100 into D is 200 cube by 12. Let me calculate this I value. So 100 into 200 cube divided by 12, which is 6, 1, 2, 3, 4, 5, 6, 7, 8. 8 sixes, 0.67. Millimeter power 4. Yes, this is the value of I. Now, what we can do here is substitute those things here. B is nothing but the width. Width at the neutral axis level, which is 100 mm. So B is 100 mm here. So B is 100. I value is this much. AY by I value is this much. AY bar is this much. F is nothing but W by 2. So because I have to apply at section A or B. So now I will write now Q max at the neutral axis level. Q max is equal to F is W by 2 into AY bar is 50,000 divided by I is 66.67 into B is 1. W, Q max is nothing but here 1.2. So shear stress should not be greater than 1.2, maximum value is 1.2. Now from this we can get the value of W. Another value of W you can get. Just let us try to simplify this. So W will be 66.67 I value into 100 into 1.2 into 2. This 2 comes to denominator divided by 50,000. So the value is 320,000. So of course this is also in newtons. Both the values should be in newtons. So in the first case we got this much 50 into this divided by 6,000. Okay, let me check once again the value. 15 into 200 cube divided by 12 divided by 3,000. So which is 3333.33 Newton. In the second case, W by 2 into A into Y bar, once again I will check. A as I said, A is B into D by 2 into Y bar is 50, correct? So this is 10,000 into 50. Sorry, this is 10,000 into 50. 10,000 into 50 is 5 lakhs. Okay. W by 2 into 50 is 5 lakhs. What was there from here? Divided by I value. Once again I will check I value. 100 into 200 cube divided by 12. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 0.67. So I into B. B is 100 only. Now this becomes now. Let me. Yeah. Now I think one more zero. One zero will be. Let's see. It comes to be 52,000. Let me check it. Let me check it. So 1.2 into 1, 2, 3, 4, 5, 6, 7, 8.67 into 100 into 2. This is divided by 5 lakhs. 32,000 newtons. Now the question is, we have got two values for W. Out of those two values, which one we have to consider? So we have to consider the lowest of these two values, because when the load becomes when the load is 3,333.33 Newton, the values of bending stress and shear stress both will be within these limits. Whereas when the load exceeds, when the load is 32,000 Newton, then what happens is bending stress value will be more. So it is more than 15. So that's why we have to consider the lower of the two values. So what I will write here is, therefore W central concentrated load. Central concentrated load that can be applied is equal to lower of above two values, which is 3333.33 Newton or 3.333 kilonewton. This is load that can be applied on the beam safely, so that the bending and shear stress values are within these two limits. So this is how. So this is other type of problem where he has given the maximum bending and shear stress values, and he has asked you the value of central concentrated load. For the same problem, if they ask you to find the UDL, other things remaining the same, if they ask you to find the UDL, then instead of WL by 4, you have to take WL square by 8. WL square by 8 is the maximum value of bending moment, and using the same procedure, here you will be getting W instead of this WL by 4, WL by 4. Oh, sorry, I have not put 4 here. Yes, 4 should come here, WL by 4. So now that value of W you will be getting slightly more. That's right. So here this becomes 4 into because WL by 4 is M. So this becomes into 4. Okay, 33.33 into 4. So the value is 13,333.22 meter. So among these two, of course, the higher value is this one only, 13,333.32, or it is 13.333 kilometers. This is the answer. So please see here, be careful here. So M is WL by 4. So W is unknown, L is 3000 mm divided by 4 into I is VTU by 12 is equal to F max is 15 Newton per mm square, Y max is 100. So this is how that 4 goes for the numerator here, and this is the answer. So 13.33 kN, up to that you can apply the concentrated load. If it is UDL, WL square by 8. So same formula, same method, same equation, but here W into L square becomes 3000 square divided by 8 will be there. Calculate W, and maximum shear stress is calculated based on maximum shear force value. Maximum shear force will be in that case WL by 2. If it is UDL, WL by 2. So here instead of W by 2, here instead of W by 2, you have to take WL by 2, where L is once again 3000. And we have to simplify, keeping the other things same. So if they ask UDL for the same problem, you have to do